All right, good afternoon, everybody. Let me turn this thing on. All right, can you hear me now? Excellent. How's everyone doing? We are getting very close to the end of 6004. So let me just give you a few updates before we get into today's lecture. The first thing is that next week we are giving you guys a break. There's not going to be lecture or recitation next week. However, we want to make sure you know that Lab 7 is due tonight and the checkoff is still due on by Wednesday of next week. So don't forget about that. The second thing is that we actually only have one more lecture after today's lecture because towards the end of the semester we basically give you the time in order to work as much as possible on your design project. We do still have one more quiz coming up, which is the Thursday after Thanksgiving, and we will put notes up on Piazza and on the website about details of quiz reviews and practice quizzes and all of that. And the only other thing I wanted to mention is that just like we've done in the past, we do offer a makeup for the third 6004 quiz. However, because of the way that grading works in this class, where there's specific point cutoffs, we strongly recommend that people try to take the quiz on time, because that way you get your score by Friday and you have 5 days from then until when the design project is due to know exactly how many points you want for a particular grade you're trying to get. If you take the makeup, we basically can't give you your score till the day the design project is due. So just keep that in mind. And any logistical questions before I get started? All right, terrific. So let's go ahead and continue our discussion of trying to improve the performance of our processor. So we said that we're going to do this by essentially allowing things to occur in parallel. And so last time we talked about issues that come up when you start to do things in parallel and the synchronization that you have to do in order to deal with them. Today we're going to talk about a different problem that arises, which is called cache coherence. So essentially, as we get into more sophisticated microprocessors, what you're going to find is that they're going to have more than one core, okay? And so essentially we're going to be able to do multiple computations in parallel. It can either be in the form of, independent threads, as we talked about last time, or it can be in the form of cooperating threads where they're working together to get a big computation done in order to basically improve the performance. And so the picture that we want you to have in mind is this picture right here, where you essentially have 4 cores, and they can work together in order to, as I mentioned, do a complicated application, make it go faster. And the way that they communicate with each other is through main memory. Okay? And so we're going to see, however, what happens with the fact that each of these cores actually has its own private cache and what implications that has in terms of making sure that they're doing the right thing. Okay, so what's the problem? What is cache coherence all about? What's the problem we're actually trying to solve? So for a second, I want you to imagine that this picture doesn't have the caches here, okay? So imagine you have 4 cores, or you can think of it as 4 processors, and they all talk to main memory. And they're going to make load and store requests to main memory, and main memory is going to deal with them in order, and it'll give each of them their response also in order. And the good thing about that is that main memory has kind of the overall view of what all the values are, and so it's keeping all the processors consistent with each other so that they compute the right thing. But now we bring these caches into the mix because we want to improve performance by allowing each of these cores to have their own private cache. And so now let's take a look at what happens and what might go wrong. So suppose that core 0 wants to do a load of address A. And so it goes ahead and asks main memory for this address, and it gets the value back, and it puts in its cache that the contents of address A are equal to 2, and now it has a valid location in its cache that represents the address A. So now core 2 comes along, and it also wants to read address A. It wants to write to address A. And so it's going to bring address A into its cache, and it's going to modify it to be equal to 3. Okay? Well, as you can imagine, now if core 0 comes back and it wants to read A again, well, if we didn't do anything about it, it's going to see that address A is in its cache, so it's going to get a hit, and it's going to return the value 2. But clearly, we don't want to return the value 2 because in the meantime, core 2 has updated the value of address A to be 3, so 3 is really what we wanted to return. Okay? And so what cache coherence protocols do is they basically deal with this specific issue so that we don't get stale values back from our caches. And you can think of, one sort of straightforward solution to this would have been that when core 2 came along and said, hey, I want to write to address A, if we had simply invalidated the copy that core 0 had, then when it went back to do the load, it would get a miss, and so then it would go and fetch the value from memory, and it would get the updated value that core 2 would have also written to main memory. And so we're going to see examples of how, what are alternatives to actually trying to implement this. So to kind of get us all on the same page, let's first define, what does it mean to have a coherent memory? Okay, so we said that if the caches weren't there, then essentially we would expect the main memory to respond to each of the processor's requests sequentially, and they would have, a global vision of everything that's happening, and it would, treat things in order. Now, when we just try to have multiple caches have a copy of the same address, we saw that this could lead to problems of stale data. So what we're going to do is, in order to avoid this stale data, we're going to ensure that only one cache at a time is given write permission for a particular address. And in addition, no cache is allowed to have a stale copy of the data. So in other words, it's impossible. We're going to make it impossible for a cache to return the wrong value, because whenever the value is stale, we will have invalidated it from its cache. Okay, so in order to actually implement cache coherence, there's two things that we need to satisfy. The first is called write propagation, and write propagation basically means that eventually any write that you do or that any processor does will become visible to all of the other processors. And write serialization means that if you're writing to the same location, these writes are serialized, so all of the processors are going to see them in exactly the same order. Okay, so first let's talk about what are our possibilities for handling write propagation. So there are two protocols that one can use to deal with write propagation. The most common one, which we're going to see a lot of today, is called write invalidate. So the idea here is basically what we've started to allude to so far, which is that whenever somebody wants to write to a particular location in the cache, then it has to be the only cache that has a copy of that location, and so everybody else has to invalidate their copy of that address from their cache. An alternative to this, which is much more bandwidth heavy, is a write update protocol, where here basically every time you're performing a write, you're going to update all of the caches so that they're all in sync with each other, as well as main memory. Okay, and so certainly that would work because it would keep things from being stale, but obviously you need a lot more communication in order to transmit all of these updated values, even in cases where a cache might not actually care about it. So we're going to see today that the most common solution is this write and validate protocol, and we're going to actually see a variety of write and validate protocols and how they work. Now, for write serialization, there's also two protocols that are used in order to deal with this. The more simple one, which is what we're going to spend most of today's lecture on, is called Snooping-Based Protocol. And the idea here is that basically all caches are observing what each of the other caches is doing and responding to it accordingly. And this is a pretty simple protocol to implement. However, it's not that scalable, because the way that it works, which we'll see in a second, is that all of the processors have to talk on a shared bus. And so as you get more and more processors involved, having them all talk to one shared bus becomes unrealistic. And so in order to deal with scalability, there are other approaches, such as the directory-based protocol, which we're just going to touch on briefly just to give you a sense for how it works towards the end of today's lecture. So, any questions so far? All right. So this is what a Snooping-based cache looks like. So the idea is you've got a bunch of processors, or cores, we can just call them processors from now on, and each one of them has their own Snoopy cache. And then the caches are all connected to this shared bus, which is also connected to main memory. Okay? And so the reason that it's called a Snoopy cache coherence protocol is because what these caches are doing is they're essentially snooping on the bus. They're listening to what's going on the bus in order to know exactly what it is that the other caches are requesting and respond to it appropriately. So how do we go about, having this snooping-based coherence? Well, there's a few things that we said we have to satisfy. So the first thing is that everything has to continue to be ordered. So the fact that we're going to be broadcasting things on a shared bus is going to, by default, give us the fact that everyone's going to see everything in the same order. Okay, and then each of the caches is going to listen to what the other caches are doing, and it's going to alter the state of its cache based on what it sees on this shared bus. So if you recall, hopefully at this point this looks very familiar. Imagine that you have a cache here, and it's got some tag bits and it's got some data bits, and in addition, we've talked so far about having valid and dirty bits, which essentially are state bits that are giving us information about the state of that line in the cache. And so from now on, we're going to, instead of just talk about these individual bits, we're going to talk about state as a whole. And so these cache controllers are going to be responsible for updating the state based on what it is that they hear from the bus, as well as based on what it is that their processor is requesting. Okay, so you see that essentially we have two things coming into this cache controller: the processor load and store requests, as well as what it hears on the bus from everybody else. And so the way that we describe cache coherence protocols is basically by defining a finite state machine that tells the cache controller how exactly it should modify the state based on what it sees both from the processor and from the bus. And so we're going to start off today by taking a look at the most simple of these algorithms, and then we'll start to make them more complex in order to improve upon performance. So let's start with the most basic one, which is called a valid-invalid protocol, or VI for short. Okay? So what happens here? So essentially, we're defining an FSM, and the FSM has two states. It's got an invalid state and a valid state, and there's 4 different actions associated with this protocol. There are 2 actions that are initiated by the processor, so the processor can initiate a read or a write. And there's also 2 actions that are bus-based, which is there's a bus bus read and a bus write, okay? So in this simple protocol, the caches that we're going to be using, we're going to assume are write-through caches. Can anybody tell me what it means to be a write-through cache? Yep.
So I just immediately write back to memory?
Yeah, so we keep main memory in sync with our caches, okay? So for this protocol, the main memory is going to be kept in sync with the caches. And the way that it works is as follows. So suppose I start off here in the invalid state. Can you actually see my mouse? Yeah, okay. I start off here in the invalid state, and let's say that my processor wants to do a load. Okay, so it's going to issue a processor read request, and that's going to have me switch from the invalid state, where I didn't have any information about the address that's being requested, to the valid state, and I'm going to go ahead and fetch that value from memory, bring it into my cache, and I'm going to set the line that holds that location in the cache to valid. Okay? Now, in addition, however, you'll notice that you have this other thing attached to this process read request. So what's going to happen in order for the other caches to know exactly what's going on is that when the processor requests a read, we're going to issue a bus read on this shared bus so that everybody else knows that this cache is requesting this particular location. Okay, so now let's say we're in the valid state, and now I have, a valid copy of the data that, of let's say address A. We'll just keep talking about address A. And suppose that my process does request another load of address A. So what happens now? Do I need to go to memory to get this data? No, right? It's in my cache. Do I need to broadcast anything on the bus? Also no, because I've basically already told everybody that I care about reading this value. And so essentially, I have this very simple state where I just loop back, I stay in the valid state, and I serve that read request from my local cache. Okay, because I have a copy of it and it's not stale. Okay? Now, if, however, the process requests a write, then remember this is a write-through cache. So what that's going to cause is a bus write to be initiated so that the write value that I'm writing to my cache also gets written to my main memory. Okay, so my main memory is being in sync with my cache. And what happens over here on the right, this dashed line here shows what is it that the other processes are doing as they're listening to things on the bus, right? So my process 1, is the one that had this process write request, and process 2 sees that, oh, process 1 initiated a bus write transaction on address A. And so what it's going to do is that if it also had a copy of address A in its cache, it's going to go ahead and go back to the invalid state so that it doesn't serve a stale value if it wants to access address A again. Okay, and we'll see a detailed example of all of this in just a second. Okay, and then the last arrow that I want to mention is just this one right here, which is if you're in the invalid state, you can actually address a write request by simply issuing a bus write transaction so that you're automatically writing the value back to memory, and you don't have to bother even changing states in that situation. So let's walk through a detailed example of how this valid-invalid protocol works. So imagine that you have 2 cores, and in all of these examples we're going to use these 2 cores, each of which has a private cache, and we're going to assume for now that the block size is 1, so we have 1 word per line of our cache. And these caches are, attached to a shared bus, and the shared bus is also connected to main memory. So now, first thing that happens is that my core 0 wants to load address A. So what's going to happen? Well, we're basically doing exactly what our FSM told us, which is we got a process read request, so we issue a bus read request. And so we put a bus read on the bus, and main memory responds to us and tells us what the value of address A is. And so now I can fill my cache, and I can switch my state to the valid state. And so I have now address A in my cache in the valid state, and I have that its value is equal to 2, okay? So now core 1 comes along, and it also wants to do a load of address A. So it also needs to initiate a bus read request for address A. Once again, the main memory is going to respond, and it's going to get the value of address A and put it into its cache, and it's also going to have a state of valid. Okay, so now both of the cores have address A in their cache, and they both know that the value is 2. Okay, so if I have additional loads of address A from either of the cores, do I need to issue any additional bus requests? No, right? I don't need to go to main memory at all, and so I can just go ahead and serve them locally from then on. Okay? Now, suppose after this that my core 0 wants to now write to address A, okay? And so the first thing it's going to do is, again, what the FSM tells it, which is that when you're in the valid state and you get a processor write request, you have to do a bus write, okay? So it's going to announce on the bus that it's about to write the value 3 into address A, okay? So what is that going to do? First thing that's going to happen is that core 1 is going to listen to or snoop on the bus, and it's going to see that that's what core 0 is trying to do. So what it's going to do is that it's going to invalidate itself. So it's going to turn that line to the invalid state. Okay, so it's as if it no longer has address A in its cache. And also, the main memory got updated with this new value at the same time. Okay? Now, we continue, and sorry. Okay, and now let's suppose that core 1 now wants to load address A again. Well, it just invalidated address A, and so when it goes to look for it in the cache, it's going to get a miss. So it's going to initiate a bus read request in order to get it back into its cache. And what's going to happen now is that it's going to get the updated value from main memory, which is now 3, and it's going to go back into the valid state. Okay? Any questions about that? Okay, so pretty simple, right? All we've basically done is we've ensured that whenever one of the caches wants to write to a particular address, it's got to be the only one that has a valid copy of it, and everyone else has to invalidate. In addition, every time we do a write, we also update main memory directly. So main memory is never stale, and it's got the latest version, and so anytime we do a load, we can get the value from main memory. But can anybody tell me what some problems with this VI algorithm is? Is it wasteful in any way? Yeah.
One in step 3, when there's a bus write, why doesn't core 1 pick up the new value from the bus write info?
It can as well, and we're going to actually see that in just a moment. But the point is that the main memory has the same information, and so whether it gets it from main memory or via the bus from the other cache, it'll get the right data in both cases. But what about any problems with this algorithm? Are we doing unnecessary writes to main memory? Yeah, right? Every single time that I'm doing a write, I'm also updating main memory. In addition, every time that I do a write, I force everyone to basically do, I do a broadcast on the bus, and then all the other caches have to do a snoop. So this is very inefficient if I'm trying to modify some private data that isn't really relevant to everybody else. So in order to improve upon this, there's another protocol which is, has one additional state, and it works like this. So we continue to have an invalid state, which means that the cache does not have that particular address in its cache. But now we split up the valid state into two states. There's a S state, which stands for shared, which means that the cache has a valid value of this address, but it's also possible that other caches have it in their cache as well. So that means that the only thing that's safe to do to this address is to read it. And the third state is a modified state, which means that this is the only cache that has this address in the modified state, which means that not only can it read it, but it can also write to this location safely, because all of the other caches would have already invalidated that line from their cache. So let's take a look at how this works. Okay, so it's basically going to address the VI drawbacks, which is that every write was updating main memory, and before we had to have a write-through cache. So this is going to support a write-back cache. Who can remind me what a write-back cache is? It means that we only write things back to the memory when we're going to evict it from our cache, okay? So MSI supports write-back caches, and it also supports doing writes locally, which means that once I'm in the modify state, if I need to do additional writes to that same address, I'm doing them directly in the cache without writing to main memory. So let's see how that works, okay? So here's my FSM, a little more complicated because now we have three states. So we've got the invalid, the shared, and the modified state. And you'll notice that basically the way that this is drawn is that the states with less privilege are on the bottom, and as you go up the states here, you basically get more and more privileges, right? So if you're invalid, then you just don't have access to the data at all. Shared, you can read, and modify, you can both read and write, okay? And on the left here, this is going to, it's basically the same as what we saw in the valid-invalid situation, but just to, since we're starting to deal with more arrows, let me be a little bit more explicit about what we're seeing here. So on the left, we draw the arrows that correspond to the processor requests, okay? So in orange here, we've got processor read and write requests, which basically have us move up in the state machine from a lower privileged state to a higher privileged state so that you can actually do what the processor is requesting. And on the right here, or these dashed lines, are the things that we see happening on the bus. So it's what we're snooping on the bus. And so this is showing us what it is that the other caches that are snooping on the bus are seeing and how they respond to what they see on the bus, okay? So essentially, when we broadcast when one cache broadcasts something on the bus, it generally means that the other caches need to potentially lower their privilege to either, from modified to shared or shared to invalid, okay? So let's work through this FSM to make sure we understand how this works. Now, notice that there's one additional action type in this FSM. So let's just quickly go through our action list. So the processor continues to just to do reads and writes just like before. And as we did before, we have bus reads and bus writes, except that now you'll notice that we have two types of bus read requests. There's a regular bus read and there's a bus read exclusive, which means I want to have the only copy of this address in anybody's cache. And in addition, the bus write is now a bus write back, meaning that we're only writing back when we're evicting it from our cache or invalidating it from our cache. Okay, so let's start off in our invalid state and see how this FSM works. So suppose that a processor comes along and it wants to read some address. It's going to issue a process read request, which is going to take that, that cache line into the shared state. Okay? In order to do that, it also sends a broadcast of a bus read request to let everybody else know that this cache is now also looking at this address. If after that it wants to then write to this address, then it needs to go up yet another privilege level. So this process write is going to go from shared to modified by issuing a bus read exclusive request on the bus. So now the key is, what do the other caches do when they see a bus read exclusive? And so that's what's shown in these dashed blue arrows here. This one that goes from modified to invalid is responding to a bus read exclusive, and this one that goes from shared to invalid also shows what happens when we respond to a bus read exclusive. So we'll start with the simpler case first. If I was in a shared state, and meaning I had a copy of this value in my cache and I see a bus read exclusive request that some other cache is making, what I need to do is I just need to invalidate my copy of this address. So I basically need to no longer have it in my cache. And so I go from the shared state to the invalid state, but because I didn't modify this location at all, I don't need to write anything to memory, don't need to do any other kind of bus transaction. On the other hand, if I was in the modified state when some other cache came along and said it wants to write, then I have to first write back to main memory the value that I had updated in my cache. So if you're in modified state and you see a bus read exclusive on the bus, then what you're going to initiate is a bus write back, which is going to write back your modified value to main memory, and then you're going to go into the invalid state, which is going to then allow the other cache, the one that made the processor write request, enter the modified state. Any questions about that? Yes?
So when you're in the invalid state and you issue a bus read, how would it know, like, other caches also has the same address? Like, it would go immediately to the shared.
In the bus read, it always will just go to the shared, whether or not somebody else has it. All it means to go into the shared is that it's possible for others to have it. But you know for sure that nobody has it in the modified state. Okay? Sorry, actually I shouldn't say that. Let me actually reiterate that. Suppose that I did a bus read and I went from invalid to shared, but there was somebody who had it in modified, then what they're going to do is basically follow this arrow right here, which is they see that a bus read was issued, so it's going to initiate a bus write back to write its modified copy back to main memory, and it's also going to move back to the shared state so that now both of these caches can have a read value, a read-only value of that location. Okay? So if somebody else was in the invalid, then you don't have to initiate any bus transaction. If they were in shared, you also don't have to initiate any bus transaction for a process read. But if they were in modified, then yes, you do have to initiate the write back before you can have it go into the shared state. Okay? All right, so let me see if there are any other arrows that I haven't covered here yet. So the last ones are these feedback into the S state, which basically show us that when we're in the shared state, we can respond to processor read locally, and also if we see bus reads, we don't have to do anything. We can just stay in the shared state. Okay? So let's, again, walk through a detailed example which makes this all make a lot more sense. So once again, we've got our main memory and we've got 2 cores, and we're going to start off with core 0 wanting to do a load of address A. So in the MSI protocol, what's going to happen is that a bus read request is issued from core A, from core 0, and it's going to go to main memory, and it's going to get the value of A, put it into its cache, and it's now going to go into the shared state with the value of address A, which is 2. Now core 1 comes along, and it also wants to do a load of address A. And so it issues a bus read of address A, and now, once again, the main memory is going to respond, and it's going to go into the shared state, and now both of them have address A and the value 2. Okay, so just like in the valid-invalid protocol, now if there are additional load requests to address A, both of them can respond to it locally without having to go to main memory or issue any more bus requests. Now, once again, suppose that core 0 comes along and it wants to do a store to address A. So what's going to happen in the MSI protocol is that it's going to issue a bus read exclusive, request. So this bus read exclusive request is going to tell core 1 that it can no longer have a shared value of address A. So core 1 has to go ahead and invalidate its copy of address A from its cache. And once it's done that, then core 0 can go into the modified state and actually update the value of address A to be 3. Okay? So now, if there's another either load or write request to core 0, it can answer it locally again. It doesn't have to go to main memory, doesn't have to do anything on the bus, because it's got the exclusive copy of address A. But if another process wants to access it, then let's see what happens. So now, let's say that core 1 wants to do a write to address A. So what's it going to do? It's going to do exactly what core 0 had done, which is it's going to issue a bus read exclusive. Okay? Now, core 0, which is in the modified state, sees a bus read exclusive, and so it has to get out of the modified state. So what's it going to do first? What does it mean if it's in the modified state? It means that it had the right to write to something, and so it can have a modified version of this value. So the first thing that it has to do is it has to write back to main memory its updated value, right? So that core 1 is going to somehow get this updated value, which is now 3 instead of 2, because main memory still thinks that the value of address A is 2, right? Okay, so we're going to write back this value 3 to main memory, and at the same time, this is addressing the question you had before, the core 1 is going to read this updated value 3 as it brings address A back into the cache. So after it's written this value back, core 0 invalidates itself, and now core 1 can go into the modified state and actually go ahead and modify it because it's got the exclusive copy, okay? So, however, notice that before it got to do that, the 3 was written back to main memory, okay? All right, so, well, what kind of problems, happen here? Well, you'll notice that in the case of MSI, it's no longer the case that main memory has the most recent up-to-date value. It's in this case we saw that main memory had a value 2 while core 0's cache had a value 3 for address A. Right? And so when another core comes along and makes a request for address A, you actually have to be careful to intervene and make sure that the response actually comes from the other cache rather than from main memory, so that you don't get a stale response. And so if we go back to our example, and now, so we're in the state where core 0 has an invalid copy and core 1 has a modified copy, and let's say that now core 0 comes again and it wants to do a load of address A. Well, remember, what's the main memory think that address A is at the moment? 3, right? So how do we deal with this? What's going to happen is process 0 is going to initiate a bus read of address A, which is going to be snooped by this core, which is going to see it, and so it's going to respond with this updated value 10, in addition to seeing that it can no longer stay in the modified state. And so it's going to write back the value 10 to both main memory, and it's going to pass it to this other cache. It's then going to go to the shared state, not the invalid state, because you can have multiple caches in the shared state at the same time. And once that's been done, then core 0 can go into the shared state and get that same updated value of address A. Any questions about that? All right, so you might ask yourself, well, what's the problem with MSI? The problem you might have noticed, or you might not have, but I'll point it out, is that in the MSI protocol, every time you want to do a read followed by or a read modify write operation, which, as we learned in last lecture, when you do things on a critical region, it's very common to read modify write, and you want to do all of this atomically. Well, if you're going to do that, in the MSI protocol, the way that it's going to work is when you go from your invalid to your shared state, you issue one bus request, which is the bus read request. And then after that, you're going to issue a bus write request as you go to the, a bus read exclusive request in order to go to the modified state. So essentially, every time you want to do a read modify write, you actually have to issue 2 bus requests, okay? And so this is very inefficient. And so we make a slight modification to this MSI protocol by adding one more state, which is called the exclusive state. And so how does this work? The exclusive state basically says that if I'm trying to read an address and there's nobody else that's currently looking at that address, then instead of getting it in the shared state, I'm going to get it in the exclusive state. And the advantage of doing that is that from this exclusive state, I'm able to then issue a write request and go directly to the modified state without initiating another bus transaction. So let's take a look at this modified FSM and see how that works. So it's starting to look a little bit scary, but let me point out that the bottom 3 states here are the same 3 states we had before and the same transitions that we've already seen for MSI. So all we're adding here is this new state, this exclusive state, okay? So what's going to happen? If I'm in my invalid state, if I do a process, if I'm dealing with a process read request, basically what happens is you issue, this process read, and you do a bus read which has all of the caches listening. And so the caches are basically going to respond if they have a copy of this address or not. So if they don't have a copy of the address, then you're in the no sharers state, and so you're going to grab that address and put it into the exclusive state. If, however, some of the caches respond saying, hey, I also have address A in my cache, then what's going to happen is that instead of going to the exclusive state, you go to the shared state, and it looks just like the MSI protocol before. But so what's the advantage if I am the only one that is trying to read and modify this location? Well, I would do a process read which causes a bus read request, so that's one bus transaction, brings me into my exclusive state. Once I'm in my exclusive state, I can respond to process reads without any additional bus transactions, just like the shared state can do. But the key difference is this, which is when I'm in the exclusive state and I get a process write request, I can, quietly go into the modified state without having to initiate any additional bus requests, okay? So then once I'm in the modified state, then just like before, I'm able to both read and write to it. And finally, the last arrow here is if you're in the exclusive state, and you see a bus read request because some other cache requested to read this address, then you're no longer in the exclusive state and you have to move from exclusive to shared to indicate that more than one cache has a copy of this address. Okay? And so it's very similar to the MSI protocol, except for the fact that you're able to save one bus request every time you do a read, modify, write. Okay? Any questions about that? All right, so that basically wraps up our discussion of Snoopy caches. And so there are just a couple other things that I want to show you today. The first is what a directory-based coherence protocol looks like at a high level. So we're not going to go into the details of it, but basically as we want to scale our cache coherence because we have more and more processors, what we're going to do is we're going to use a directory-based coherence scheme. And the way that this works is essentially you take your main memory and you split it up into individual chunks, and each processor is responsible for one chunk of memory. Okay? Now, every time somebody wants to do a load or write to a particular chunk of memory, what they're doing is they're basically sending a request to the processor that's in charge of that portion of memory. Okay? So that processor not only is in charge of that block of memory, but it also has a directory which tells it all the information about which caches currently have copies of data that's associated with this portion of memory in their caches and what the state of each of those caches is. And so the processor that's responsible for that portion of memory is able to respond and also initiate any additional requests to the other caches to say, you know, if someone's requesting to be in the modified state and someone else had it in a shared state, in a modified state, then they need to go ahead and write back their value before this other one can go into a modified state. But the key, though, is that the communication that happens is point to point here. And so you can do a bunch of these point-to-point communications in parallel rather than having to have one monolithic bus that all of them are listening to at the same time. Okay, so that's basically how directory-based coherence works. And of course, if you want to know more about it, you can take some of the more advanced computer architecture classes. And just to finish off today, I want to just, you know, show you that as you continue to explore these things, you're going to have, you know, more and more issues to try to deal with. And we're just going to point out one in this last slide here, which is, you know, for today's lecture, I went with a simple explanation that we had one word per block, okay? And so we didn't get into the intricacies of what does it mean when I have multiple words in my block. But imagine, you know, which is the more common case, that I do actually have a line with multiple words in my block. And so now you can imagine a scenario where, let's suppose that process 1 is writing to word I, and process 2 is writing to word K, and both of those happen to live in the same line, but it's not actually the same location that I'm trying to write to. So every time I'm going to try to modify one of those, I'm going to ping pong between which one of these caches has this line in the modify state, right? Because my state is per cache line, not per cache word, okay? And so I'm basically adding an unnecessary constraint of switching back and forth between who owns this line when all I'm actually trying to do is write to two distinct words. And so this is just one example of the types of complications that arise as you start to deal with cache coherence, and there's many more of these, but today we introduced you to essentially the basic algorithms of how we go about dealing with cache coherence at a high level in order to give you a sense for how it works and how modern processors are actually doing it. So with that, that's it for today. So happy Thanksgiving. We will see you not next Tuesday, but the following Tuesday. Make sure to finish Lab 7 and get your checkoffs, however, before Thanksgiving. Thank you very much.